This is the finalized CAD drawing I developed for 4th year engineering science capstone. So here we have a stepper motor which is mounted on a 3D printed part. The shaft of the stepper motor feeds into a shaft adapter which then connects to a lead screw. On the lead screw we have mounted another 3D printed part, the large nut connector, which is mounted on 2 linear bearings. Underneath the large nut connector is a nut on the lead screw, so when the lead screw turns, the entire platform moves down the lead screw and these 2 supporting guide pins. So on the large nut connector we also have another mounted stepper motor which drives another lead screw so that we can move this other 3D printed part, the small nut connector, in the Y direction as well. So this means that we can move the entire platform in the XY plane. On the other end we have a final 3D printed part for the supports, the large pillow block stand, where we have mounted the other end of the guide pins and the lead screw. So on the small nut connector we have a solenoid mounted and a pin solenoid connector, so that when the solenoid is engaged we have the pin is pushed down through here into the surface. Having the CAD model was really helpful for the specific dimensions of each piece, knowing how it had to come together and being able to figure out how to shape each 3D piece to make it work. Alright, so first we'll go over the 3D printed pieces, including the large nut connector, the small nut connector, the large pillow block stand, the motor mount, the solenoid probe connector, and the solenoid small nut connector mount. Then we'll go over the aluminum stands, which support the shaft holders for the lead screw and the guide pins. Then I'll talk about some of my non-capstone related Solidworks projects, including my thesis where I built an ultra-high pressure anvil cell, and a second project that I worked on my own for an automated bending robot. Alright, this is our first 3D printed part, the nut connector. This is designed to connect the nut, which goes in the lead screw and fits right in here in this gap, and connects that to the pillow blocks, the linear bearings, which are attached through bolts that'll go through these 4 holes here on this side and these 4 holes on this side. From there we can attach the aluminum piece on here, which holds the shaft holders for the guide pins and the lead screw going the other way in the Y direction. Now we have 4 holes here and a center hole to fit the motor, which will be mounted here and wired up so that we can drive the lead screw that goes in this direction. So these holes here are 4 millimeters. The actual screws that go into the motor are actually 3 millimeters, but through testing and prototyping with the 3D printing, it seems that 3 millimeter screws fit perfectly in 4 millimeter printed holes. Now we have these holes here which fit 1/4 inch bolts. This is to attach the flange to the nut connector, so that's what actually keeps it from rotating. Alright, so here you can actually see us printing the 3D model for the nut connector. So the first time we did this, it actually took 4 hours to make it low resolution. When we actually tested it out, it had some problems. We reprinted it at high resolution, which took us about 13.5 hours. So you can see the actual one right here on the frame. And this is the one we're actually using right now. This is the previous prototype that took 4 hours to print. You can see that it's a bit flimsy in the frame for the motor stand. And it has some other problems, like this edge here is a bit warped because of the low resolution. The scaffolding wasn't quite as accurate as we'd like it to be. This is the second 3D printed part, the small nut connector. It's almost the exact same as the large nut connector, except it fits on the smaller lead screw. You can see we have another semicircle extrusion here that'll fit on the smaller nut going in the Y direction. We also have holes that can be secured to the smaller flange as well. It is extended slightly in this direction to fit on a second attachment which contains a U-bolt for extending the solenoid down to the probe solenoid connector. So we can see the small nut connector here. It's connected to the flange in the same way as the large nut connector and to the linear bearings. This is the second, well, there's another 3D printed part here. This is temporary until we finalize the design with the actual 4 probes that will go in the live product. The solenoid can be connected via a U-bolt to the small nut connector in this secondary 3D printed part, which is attached through this hole here. So it is held perfectly vertical to the surface. Alright, and here's an image of the final 3D print job for the small nut connector. So this is the third 3D printed piece, the large pillow block stand. So this stands opposite the small nut connector and holds the aluminum surface, which will hold the shaft holders and the rotating bearing for holding the lead screw. So these four holes just screw it into the pillow block, which stands opposite the small nut connector on a guide pin. And these four holes are for securing the aluminum to the large pillow block stand. So we can see the large pillow block stand in the assembly here. It's attached to the aluminum piece, as we said before, which holds the smaller lead screw and guide pins, which go into the other side, and the large nut connector. Yeah, so this is a minor piece. It just needed to be the right height to fit the aluminum and the shaft holders on it. So here we have the large pillow block stand printing at the Toronto Reference Library. And we also have the final printed piece that we used in our design. This is the fourth 3D printed piece, the motor mount. So this holds the first motor, which drives the large lead screw. The motor can be mounted right here and screwed into these 4mm holes, while the shaft goes through this hole into the lead screw through a shaft adapter. And it can hopefully turn the lead screw and make the nut go down the track. So we have these holes here, which are used to, actually all four of these holes are used to secure the motor mount to the frame. And here we have the motor mount printout that was used in our final design. This is the solenoid probe connector. The solenoid plunger can be inserted at the top here and then bolted to the 3D printed part. Then the probe itself can actually be inserted here through this hole at the end. It can't be fed the other way though because of the wiring at the top on the solder cup of the probe. We actually have an extruded cut as well here where you can put your finger to push the probe in and then feed it through this hole at the bottom. Then we have two holes here on the bottom where two bolts can be inserted, and these will hold the probe in place so it can be placed at an adjustable height. Now we can see the solenoid probe connector here on the actual model. It's attached to the solenoid small nut connector mount through a U-bolt here. And then once the solenoid is disengaged, the plunger will be pressed into the probe connector, which will push it down into the surface. The probe itself is compressible, so it will be pushing the surface as far as it can go. And here you can see the solenoid probe connector printing at the Toronto Reference Library. Here we have a prototype for the solenoid probe connector. You can see it's missing the bottom part here, where you can actually press in the probe tip, so you can slot it in through here. This one ran into a few problems. One, these holes here were too small, so I had to widen them with the Dremel tool. The plastic ended up getting cracked, so the model was unusable. In a separate copy, I ended up having to make this hole larger with a Dremel tool to fit the solenoid plunger because these holes were too low. This melted through the plastic here, and the end just snapped off. The actual model we used in the final design included a thicker amount of plastic here and a much wider extended frame for the probe connector. And here you can see the final probe connector attached to the solenoid. This is the last 3D printed part, the solenoid small nut connector mount. So this can be attached to the small nut connector, and then the solenoid can be secured through a U-bolt in these holes. So the reason for having this part separate from the nut connector is because of the Toronto Reference Library's limit for 2-hour printing sessions. Here we have the large aluminum stand with the shaft holders on top. The shaft holders are then bolted to the extrusion through the aluminum stand. Now we can see how the shaft holders are mounted on the frame with the large aluminum stand underneath. Now we move to the small aluminum stand, which is mounted on the large nut connector here. This model is very similar, except it has these extra folds here for mounting on the large nut connector. While the aluminum stand is bolted to the large nut connector, the shaft holders are only bolted to the aluminum stand. This makes it easy to align the shaft holders so that the guide pins and the lead screw are perfectly parallel. Ideally, this could have also been done with a large aluminum stand with a 3D print. However, this would have required large-scale changes to the model, and we were already late in the design cycle. In addition, the 3D printed piece may have been too flimsy and would have required several design iterations before getting it right. The last piece is the single aluminum stand. This piece is just a simpler version of the large aluminum stand. Alright, now I'll talk about my non-capstone related Solidworks projects. First I'll go over my thesis, which is in high temperature superconductivity, and then I'll talk about my automated bending unit I made for myself. Alright, this is the anvil cell I designed for thesis. It can be used to place samples under pressures up to 100 kilobar, and then the critical temperature of the superconducting phase transition can be measured as a function of temperature and pressure. So as for the construction, it's split into 3 parts in this assembly. First is the top, then we have the wall, and then the bottom. So you can see these anvils here. These actually interface in the middle at a gasket where the sample is placed, and then they can put the sample under pressures between 50 and 100 kilobar. So let's look at the top here. You can see it has 8 holes here. So you can put screws through the entire assembly through these 4 holes in the wall, and you can rotate the top to change the position of the wires, which are fed through these holes in the top right here. There is also in the top of the wall a space here for the wires to go through as well. When the entire thing is screwed together, you can see there are also 4 holes in the bottom which match up with the wall, which holds the entire cell together. There are also 4 holes here on the side of the bottom. When this is placed in here, the holes match up with these ones in the wall, and then grub screws can be placed in here to change the position of the bottom anvil, which there's about 0.5 millimeter of play to actually move that around. The point of moving it around is that you can align the 2 anvils. You can see we have 2 viewing holes. Both of them are at 90 degrees to each other. There's one here and one over here. So you can screw in the bottom anvil to make sure they're aligned with the sample and the gasket. So the anvil cell was limited in size by the probe, which is dipped in liquid helium, and the anvil cell has to be attached to it. So there's a strict limitation on the diameter. Then each of these holes had to be specifically sized so that we could fit 4 millimeter screws in them, which is enough to withstand pressures up to 100 kilobar, given that the screws are under tension when the anvil cell is placed under pressure. The anvils themselves are made of tungsten carbide, so you can see them here. I counted them for the model. This anvil cell was made specifically for these anvils with these dimensions. So the entire model had to make sure that these anvils fit in here, given the maximum constraint on the diameter because of the probe size. So here's a 3D print of the finalized design. The real thing was made in beryllium copper because of its hardness and machinability. So you have it disassembled here, and we also have 2 images of it being put together. Alright, so this is the automated bending unit I designed for a friend. So this gave me a lot more experience using Solidworks, including the wrap and draft features. I decided to make it just because I really enjoyed using Solidworks, and I got a lot of experience in Thesis and Capstone. So I actually started using Solidworks this term, so this was a great experience for me. I really enjoyed using the software, and I hope to keep using it in the future. What I want to do is continue on the automated data collector so that I can design a fully functional probe module with adjustable positions for the probes so that we can finish the design of the device. Alright, thank you very much. Now I'll leave you with a bonus clip for fun.